So quantum computing is a rapidly changing space. We've seen just in the last 3 days, NVIDIA's CEO Jensen Huang said that quantum computing is at an inflection point. We've seen IONQ make incredible acquisitions, including Oxford Ionics and LightSync. Amidst all that, we saw that IBM, an often undervalued or overlooked company in the quantum space, announced a fault-tolerant quantum computer coming in 2029, and we're halfway through 2025. So they put out a great video, and I wanted to do a little bit of a react to that, but I just wanted to show you really quickly IBM's quantum roadmap. So IBM posts this on their website, and the reason I want to talk about IBM is a couple things. One, this was my dad's first job out of college. He worked at IBM back when they were building PCs, and now as an investor in IBM, I love that they're still pushing the boundaries even 40 years later. So by 2029, and what we're going to be talking about today is they want to build the first fault-tolerant quantum computer, which will be available to clients and allow execution of 100 million gates on 200 qubits. I want to show you guys that IBM is one of the only quantum players right now that is reporting significant earnings from quantum specifically. So IBM has booked $1 billion in revenue from quantum technology with expectations for substantial future growth as the company focuses on transformative technologies like quantum and AI. IBM's strategic investment in quantum and AI are central to its growth, highlighted by the launch of advanced quantum computers and a new collaboration to establish the National Quantum Algorithm Center in Chicago. We saw just 2 days ago the announcement from IBM that they're doing this large-scale fault-tolerant quantum computer at a new IBM quantum data center, and we're going to be able to actually see what that looks like. They're building this huge data center and really putting a lot into their quantum computing. The system will use 200 logical qubits to run 100 million quantum operations and serve as the foundation for a future platform. IBM Quantum Blue, which is designed to scale 2,000 logical qubits and 1 billion operations. So that's a future machine. So this will be the first iteration. I thought this was really interesting and I highlighted it. This center that they're building in New York, we're going to see some footage of it, is expected to perform 20,000 times more operations than today's quantum computers. To represent the computational state of an IBM Starling would require the memory of more than a quintillion of the world's most powerful supercomputers. I don't even know how big that is, but that sounds like a lot of supercomputers. Our expertise across mathematics, physics, and engineering is paving the way for a large-scale, fault-tolerant quantum computer, one that will solve real-world challenges and unlock immense possibilities for business. Very exciting. Very quickly, I wanted to show you that IBM is at an all-time high on its stock chart, and it hasn't even really got the huge revenue that they're expecting to come from these quantum computers in the coming years. So they're really a sleeping giant, in my opinion, in this whole quantum race. Now let's watch, and I'll do a little bit of a react, and then we'll get out of here.
Quantum computers are widely expected to solve problems that we can't solve with classical computers. Simulations of molecules, analyzing structured data, optimization, and search problems. IBM has a long and rich history of successfully taking many ideas to a full-on product. Quantum computers will be no different. It's been a really incredible journey. I joined here almost 19 years ago. We were basically trying to work on just single qubits and showing signs of life, trying to get them entangled. Did we think it was likely back then to get to where we are today? No, but it was our goal to keep making progress, solve one problem at a time. And now looking back, this is where we got us today, building the world's most powerful quantum computers. We believe we have the only credible plan to build fault-tolerant quantum computers. We're so confident, we even put a date on it. Our first fault-tolerant quantum computer, Starling, arrives in 2029 with 200 logical qubits capable of accurately running 100 million quantum logic gates. Then, in 2033, we get BlueJ, a fault-tolerant quantum computer with 2,000 logical qubits capable of accurately running a staggering 1 billion gates.
So, really quickly, what is so important about a fault-tolerant quantum computer? So it enables, so I'm just did a quick search here. Fault-tolerant quantum computing is crucial because it enables the creation of large-scale quantum computers that can solve complex problems beyond the reach of classical computers. It involves developing error correction codes, fault-tolerant algorithms, and hardware improvements to make quantum computations reliable. This is necessary because qubits are highly sensitive to their environment and are prone to errors, which can be detected and corrected in real time, according to IBM.
We're building the data center to house the system right now in Poughkeepsie, New York.
This thing is huge.
I'm a senior research scientist at IBM, and I do research on gate errors and quantum hardware. Quantum computers apply quantum logic gates to quantum bits, or qubits, to perform complex calculations. If we can run more gates on more qubits, we can make our calculations even more complex.
Point we call quantum utility. Quantum utility means that these devices can no longer be simulated with brute force classical techniques. This happens at around 100 qubits or so and a few thousand gates. And we're within reach of getting to 15,000 gates. But we're still a far cry from what we need for the most demanding computations. In order to implement hundreds of millions or even billions of gates, we need a fault-tolerant quantum computer.
My goal is to get useful quantum algorithms to actually run in the gates inside of this error-corrected quantum computer. Currently, the challenge of getting anything to happen on a quantum computer is errors. First, we need an error-correcting code, where the computational overhead grows only mildly as complexity increases. An error-correcting code takes many error-prone physical qubits and entangles them to encode high-quality logical qubits, which have less error. These logical qubits have error rates that decrease exponentially, with a polynomial increase in the number of physical qubits.
Next, we need the error-correcting code to have a syndrome extraction circuit and an efficient decoder that is fault-tolerant. The code acts as a fault-tolerant memory that stores quantum information and protects it against errors.
Finally, we need the ability to perform arbitrary quantum circuits using a universal gate set, which requires preparing something we call magic states.
Of it is being able to scale, but at some point, we just run out of real estate on a piece of silicon. And so the approach that we've taken is we've designed a modular architecture made up of code blocks representing 12 logical qubits, each connected to a logical processing unit and universal adapter to define a single module. This is really
cool.
The logical processing unit implements simple gates. The universal adapter allows entanglement between modules. We can connect the modules together and scale the system size in a straightforward way.
We haven't solved all the experimental challenges to realize this architecture yet, but everything we're doing today is geared towards making sure that we can achieve them. We need C couplers for long-range coupling within chips, L couplers for long-range coupling between chips, and more. But we've already demonstrated prototypes of these technologies, and combining this with our modular architecture gives us confidence we have a realistic path to practical fault-tolerant quantum computing.
We've baked this new architecture into the next 4 quantum processors on our innovation roadmap. We start in 2025 with the IBM Quantum Blue, an important test vehicle and first demonstration of the technology required to run our error-correcting code. In 2026, Kookaburra will be the first quantum processor that will use our logical processing unit and QLDPC codes to demonstrate the quantum memory and simple gates. In 2027, we'll introduce Cockatoo, a quantum processor that will allow us to test the universal adapter connecting multi-gates and an integrated real-time hardware decoder. Everything is coming together, and we really have a plan. We have a strong quantum research team and advanced semiconductor technology expertise, so at any moment we have over 20 device types being built across multiple fabrication facilities and new quantum devices in fabrication every 15 to 20 days. This means we're moving much faster than anyone else in this space. We stand by what we said. IBM will deliver a fault-tolerant quantum computer to our clients by 2029.
Very nice, very nice. And take a look just at the sheer level of construction, like this B-roll they're using, the size of these machines, and the complexity of just the engineering that's going into this. When they say nobody else is doing this, that's quite the claim. But I haven't seen it personally, so I tend to believe them. So really what we see from IBM is we know that IBM isn't just a quantum computer company, but we see they're very strong in quantum computing. They've already produced revenue in quantum computing, and they're building a fault-tolerant quantum computer by 2029. So that's 3.5 years. That's within this decade. And pretty incredible that if they are able to achieve this without any major barriers. So we will see how this all turns out. But IBM is looking like a very strong quantum player. I just thought I would get on, do a little react to this video. If you like content like this, if you like staying informed about quantum and other stocks in the market, give me a like. And if you want to, also subscribe. All right, guys, have a great day.